My name is Aimee Sutton. I'm a product manager at Synopsys. I'm co-presenting with my colleague Weihua, who is a solutions architect. He will join us later. And the topic of our presentation is using hardware-assisted verification to verify a complex RISC-V design. All right, so let's get started. So RISC-V is evolving. Today, we have RISC-V not just used in microcontrollers, but in more complex applications like even data center and AI. I mean, these might not be the predominant application, but RISC-V is there. So with the evolution of RISC-V and these more complex designs, we have different verification challenges. We have multi-core designs, we have multi-level cache hierarchies, virtual memory, and things like AIA, Advanced Interrupt Architecture. All of these present new verification challenges. And new verification challenges require different verification techniques. So we don't just need test stimulus that's based on an understanding of the instruction set architecture. Of course, ISA verification for your implementation is still important, but in addition to this, we need more complex and longer running tests in order to get the design into interesting states, such as when caches or internal buffers are filled. Because it's when the design is in these interesting states that we can start to expose microarchitectural bugs in addition to architectural issues. And going along with these longer running tests and more complex test stimulus, we need a way to execute those tests so that verification can be done in a reasonable amount of time. Right? So it's often stated that to verify a high-end RISC-V core takes a quadrillion cycles. And this is just unobtainable in a platform like RTL simulation. So that's why we are now exploring hardware-assisted verification. So when we were looking for a design to test out our hardware-assisted verification solution, we looked to the open source community for a complex RISC-V design. And the one we chose was the XiangShan design from BOSC, or Beijing Open Source Chip. This is a very active open source project, and it's a good example of the type of verification challenges that you find with RISC-V designs today. So as you can see from the diagram, this core has instruction and data cache and a shared L2 cache. It supports the AIA standard, and it also has virtual memory. So this is a good example of the type of challenging RISC-V design that we are targeting with our solution. We did manage to get this design up and running with our solution, but due to some cache issues, we had to eventually switch to a different design. My colleague Weihua can give you more details about that. Okay, so if you remember back to the first slide, in our verification requirements, there are two key components. We need complex test stimulus, and we need a fast execution platform. And the complex test stimulus component comes from Sting. Sting is a bare metal generator of self-checking tests. It can work in a variety of different stimulus mechanisms. So it can generate constrained random stimulus, longer workloads, directed tests, and real-world scenarios. And all of these can be self-checking, and because they are bare metal ELF files, the tests are portable among different execution platforms from simulation, but also in emulation and FPGA prototyping platforms, which is the area that we are interested in. Sting also includes a library of over 100,000 test fragments. And so these are code fragments that can be mixed in with the different types of stimulus, directed tests, random tests, in order to create really interesting scenarios. So the component of sting stimulus that we are focused on with this solution are the workloads. So those are the long-running, more complex tests that target the kind of RISC-V designs that we are focused on with our solution. Right? And in terms of workloads, some examples of the kind of workloads that we are generating are tests for atomics, atomicity, memory ordering tests, weak memory ordering, and litmus tests, constrained random tests and constrained random traffic, and also cache coherency scenarios like true sharing and false sharing. So we can generate all of these type of workloads, but they need to be run for a significant period of time in order to really get the microarchitecture into those interesting states where we can find microarchitectural bugs in addition to architectural bugs. And so that goes back to the requirement where we need a fast execution platform to make sure that we can get this verification done in a reasonable amount of time. So now we'll go to the actual solution that we've developed. And I will give you a high-level overview before passing the presentation over to Weihua to give you more details. Okay. So our solution, HAV test solution for RISC-V, is built around hardware-assisted verification. And what that means is that the design under test is synthesized and realized on a set of FPGAs which form part of a tool for emulation or FPGA prototyping. And examples of this type of hardware-assisted verification platforms are the Synopsys, ZeBu, and HAPS platforms. Right? So it's the fact that the design is synthesized that allows you to run it at much higher rates of speed. The other component of our solution that I mentioned before is Sting and the generation of self-checking tests. What makes these tests self-checking is that we can use a reference model to embed the self-checking results inside the ELF file. So they can be self-checked even on a platform that doesn't have any visibility to the outside world. Right? And now the challenge for us is that we now need to keep up with the speed of hardware. Right? So we actually need many copies of Sting running in parallel and a solution to be able to stream the test data into the memory on the hardware platform such that the hardware is never idle and waiting for tests, but executing continuously in a cycle of test generation, execution, and checking. All right. And with that intro, I'll pass it over to Weihua. He can tell you about a little more details about the implementation of the solution and the kind of results that we got when we ran it on some different designs.
Yes, thank you. Yeah, thanks a lot, Aimee, for introducing the challenge for the RISC-V verification, as well as a short introduction about our HAV test solution. Here, I want to spend a little more time to give some more details about our solution. This HAV test solution, we are using Sting to generate the tests. Specifically, we are using Sting SRM, Sting Regression Manager, to generate tests. SRM can generate a lot of tests for RISC-V. And in this solution, we expect user to using SRM, running multiple SRM in a computing farm so that we can generate many tests. The streaming interface is actually part of the ZeBu test bench. The streaming interface will pick up the test generated by Sting and load it to the ZeBu box where the DOT is running on the ZeBu box. And on the ZeBu box, we can have a RISC-V systems running. And there's a test management program. This test management program has a protocol or handshake with the streaming interface and managed to run the test one by one in a loop. So you can see the string generation and the execution actually running in parallel. And finally, the test result is written to a log file, which with the result of each test status is failed or passed. Now, the method we explained here, the string method, can provide a better performance when compared with a traditional emulation from different ways, from different reasons. For example, this streaming method will avoid the reinitialization of the ZBOO for each test. Another thing is like it will avoid the redundant configuration cycle for each test because it will not stop your test. It will run your test one by one in a link. And as I mentioned, with this method, you can run string tests and the ZBOO execution in parallel. So, and if you generate so many tests, it's been running forever for you in a regression mode. So we evaluate the performance with this streaming-based method, and with 70 string tests. In the streaming mode, we can finish in about 4 minutes. And in the traditional mode, it takes about 16 minutes. Please note that this performance improvement is an add-on to the performance improvement of emulation compared with a simulation. We run a string test on the XiangShan 4-core design, and we see more than 6,000 emulation performance improvement when compare emulation with a simulation. And this 4x performance with the string method is add-on that performance improvement. So now, this streaming-based test solution provides several ways to let the user to debug failed tests. For example, it allows the user to run that specific test in the streaming mode, but there's a chance you cannot reproduce a failure because if you only run that test, the microarchitecture is still in a clean state, right? Sometimes you may not be able to reproduce a test failure. The solution we provide here allows the user to run the same test multiple times. You can specify 5 times, 10 times. You can check if it can reproduce a failure. If they still cannot reproduce the failure, it may be because of the failure is related to a sequence of tests. So this method allows you to specify you run a specific sequence of tests. Like the example we listed here, our target test is sting.m000, but we want to run this test and 6 tests before this one. So this is a result. You can see we will run 7 tests in a sequence, and we hope this will finally reproduce a failure. Now, how to debug the test failure? Usually, the hardware engineer will use a waveform to debug it, but the software engineer, Sting-based test is a software-driven verification, right? Software engineer will debug a test, usually look at the instruction, look at the register, etc. So if we can debug a test from both the viewpoint of software and hardware, we may be able to figure out the root cause quickly. The Verdi software hardware actually provides this kind of capability. During the emulation, we will dump the instruction, like the PC instruction register, this trace log, as well as the hardware waveform. Then in the Verdi hardware software debug, the tool, it will provide the capability to let the user to debug the test both in the viewpoint of software. You can set a breakpoint. You can going forward, backward. Then you can also look at the waveform, and we set up the synchronization between software and hardware automatically. So you can debug it both software and hardware. Yes, thank you. And we have a planned list for the future development. First, integration in parallel fast process model and the checking. This is popular in simulation world. We want to integrate in this hardware assisted verification platform. We want to integrate the functional coverage, and we have some idea about even provide a better performance which we are working on, and some debug automation technologies. Now, before we end the session, let me give a very short summary. We believe that HAV now plays a critical role in the high-quality RISC-V verification because of high performance. And this HAV test solution we presented here, we will integrate high-quality test generation from Sting and the HAV platform, and it can provide even a better performance. Last one, the hardware-software debug, the capability already provided, will help the designers to debug the test from both software viewpoint and the hardware viewpoint, and we believe it will help the user, help our customer figure out the root cause quickly. That's all the things. Thank you very much. And by the way, we have a demo in Synopsys booth downstairs. It will show how we deploy this in our ARC-V processor. And you're welcome to visit, and we can discuss more details. Thank you.
Can you hear me? Oh, right.
Yes, absolutely.
Hey, this is Darshak from Tenstorrent. So I think there were two main themes here. You had longer running test cases and the self-checking part. So I have a question on each of them. How do you, I think you talked about you are running a reference model for self-checking purposes. Is the reference model run while generating the test case or on the test bench side while running the test on Zebu test bench? The second question is on the long-running part. Are the test cases statically generated, which means you have to generate longer test cases and it will have bigger memory footprint, or they actually generate longer sequences at runtime?
Would you like me to answer? I'll answer the first part, was about the use of the reference model. So that is done when the test is generated. Okay? And the second one was, are the long-running sequences generated dynamically? Do you have a good answer for that, Weihua?
Sting has both capability to generate tests. For most of the users, they generate statically, so they can run insert the self-checking in the tests. But Sting has the capability or the parameters specify how big the test can be, right? So there's a parameter you can specify to generate long test, short test. Thank you.